this video, we're going to talk about heating and cooling curve of a substance. The learning competency for this video is to determine and explain the heating and cooling curve of a substance, and below are the learning outcomes. Let's start with a review of the phase changes. Phase changes are basically the transformations from one phase of matter to another, right? Phase changes involve a change in energy, and energy here is either released or absorbed. Just by looking at this diagram, you will already know what these labels represent. For example, melting. Okay, melting is a phase change from solid to liquid. And applying the concept of phase diagram from the previous video, you will have to pass the solid liquid equilibrium line. So here, when ice melts, energy is absorbed, and we call it an endothermic process. So what is an endothermic process? It's from an ordered arranged phase to a disordered or a less ordered arrangement. Okay, so all the processes going to the right are endothermic processes. So we have vaporization and sublimation. Now going back, we have gas to liquid, and we call it condensation. Okay, condensation is a phase change from gas to liquid. So it's from chaotic or random arrangement to a more ordered arrangement like a liquid. So we call this an exothermic reaction. Okay, so to easily memorize this, just remember exo, external, okay, endo, internal. So exo, the heat is going outside, okay, endo, the heat is going inside, or the heat is absorbed. Okay, all the process going to the left are exothermic processes. Okay, now the question is, how does a change in energy affect phase changes?
I think we should have that conversation.
To answer that, let's have a scenario. So imagine having blocks of ice and you put it over a Bunsen burner. Okay, so when the system, or ice in this case, is heated, energy from the heat or the Bunsen burner is transferred into it. Now, there are two things that can happen. First, the added heat increases the kinetic energy of the particles, so the particles move faster. That increase in kinetic energy is accompanied by an increase in temperature. Or, the added heat is used to break attractive forces between particles. So in this case, there is no observed increase in temperature, and often there is a change in the physical appearance of the substance. Okay, so there is a phase change. In the first scenario, you don't have a phase change, just increase in temperature, but here you have a phase change. Okay, so please remember this. Now, going back to the heating of ice cubes. Some might think that the temperature goes up smoothly, but that's not what happens. If the temperature of a material is monitored during heating, it varies with time. And the plot of temperature versus time is called the heating curve. Okay? And the heating curve looks like this. So let's talk about it more. Notice that in general, the temperature goes up the longer the heating continues. Okay? And you can see here three slopes. You have A to B, C to D, E to F. So remember, the slopes happen when there is temperature change. You can also see flat segments. We have B to C and D to E. Remember that the flat segments happen when there is phase change. Transformation of phases. Okay, please remember this. So let's start with AB. Between A and B, the material is solid. Okay, so the heat supplied to the material is used to increase the kinetic energy of the molecules and the temperature rises. So this is the first scenario a while ago. So the first change of state BC is melting. Here, the temperature stays the same while a substance melts. But the heat energy is now used to change the arrangement of the molecules. So the heat energy is not being changed into kinetic energy. So this is the second scenario a while ago. For water, this temperature is 0 degrees Celsius. Why? Because the melting point for water is 0 degrees Celsius. So over the course of this line segment, from here to here, both liquid and solid exist in various ratios, starting at 100% solid and 0% liquid at point B, going to or ending at 0% solid and 100% liquid. So all the points here will have their own ratio. So in the middle, you will have 50% solid and 50% liquid. Okay? At point C, all the material or substance has been changed to liquid. Between C and D, the heat supplied is again used to increase the kinetic energy of the molecules. So you have increase in temperature again because this is a slope, remember? So the liquid here is heated until it reaches point D, which is the boiling point. So the second change of state, DE, is boiling. Here the liquid is still being heated, but the extra heat energy does not change the temperature nor the kinetic energy. Okay, so the heat energy here is used to change the arrangement of the molecules to form a gas. For water, the temperature is 100 degrees Celsius because the boiling point for water is 100 degrees Celsius. So over the course of this line segment, both liquid and gas exist in various ratios, starting at 100% liquid, 0% gas, and ending at 0% liquid and 100% gas. At point E again, it's all gas. And between E and F, the gas is heated and the heat energy increases the kinetic energy of molecules once more. So the temperature of the gas increases. So you have to remember that different substances have different melting points and boiling points, but the shapes of their heating curves are very similar. For example, the heating curve of iron. So iron metal melts at 1538 degrees Celsius and boils at 2861 degrees Celsius. But the shape here is almost the same. You have one slope, then segment, slope, segment, slope. 5, just like this one. Now for each phase change of a substance, there is a characteristic quantity of heat needed to perform the phase change per gram or per mole of material. The first one is the heat of fusion. It is the amount of heat per gram or per mole required for a phase change to occur at the melting point. So remember, fusion, melting point. So like melting points, heats of fusion are influenced by the strength of attractive forces that exist between particles in the solid. Okay? So meaning, the stronger the attractive forces that hold the particles of the solid together, the larger is the heat of fusion. Next, we have what we call the heat of vaporization. It is the amount of heat per gram or per mole required for a phase change to occur at the boiling point. So if you remember from our previous videos, both the boiling point and molar heat of vaporization of a substance are influenced by the strength of attractive forces that hold the particles in the liquid state. If you know the total number of grams or moles of material, you can use this to determine the total heat being transferred for melting or solidification. So for melting, you have these equations. Heat is equal to m times the heat of fusion, or heat is equal to moles times heat of fusion. So heat is also symbolized as Q. M here is mass in grams, and this one is a constant. But this one is commonly used. So this is moles of the substance times the heat of fusion. So if you're given mass in grams, you have to use the molar mass to convert it or to get the most of the substance. Okay, so for boiling, you have this equation. It's the same. What changed is the constant. You will now use the molar heat of vaporization. Okay, now you have solid to liquid. You also have liquid to gas. Now you're missing one conversion.
Oh, what? Wait!
It is the direct conversion from solid to gas, and we call it sublimation. So we also have the heat of sublimation. The heat of sublimation have the same formula. So Q is equal to M times heat of sublimation. So how do you get this one? So remember, you want to directly convert this to this one, right? And to get from here, you will pass the heat of fusion and heat of vaporization. To get heat of sublimation, if it's not given, you just have to use the heat of fusion and the heat of vaporization. So heat of sublimation is equal to heat of fusion plus heat of vaporization. Okay, so this question is not really common. Okay, so let's try to solve some problem.
Na-vertigo ako.
How much heat is necessary to vaporize 685 grams of water at 100 degrees Celsius? So the heat of vaporization is 540 calories per gram. The first thing that you need to do is to write the given. So we have 685 grams of H2O. We also have the heat of vaporization, which is equal to 540 calories per gram. Then you write the formula. Q is equal to M times the heat of vaporization. So this is equal to 685 times 540 calories per gram. Cancel the units, you will get calories, and this will give you, or to follow the correct significant figures, as simple as that.
Why?
The heat of vaporization here is in calories per gram. If you are given moles, then you have to convert this to moles. Okay, let's have another one. How much heat is necessary to melt 55.8 grams of solid water, or ice, at 0 degrees Celsius? The heat of fusion of water is 79.9 calories per gram. So there's no need to convert this to moles. So write the given. You also have the heat of fusion. Then write the formula. Substitute the values. Then cancel the units. You will get calories. This will give you 4,460 calories. So check the significant figures. You have 3 here and you have 3 here. This one is insignificant, so this is our final answer. Okay, now what if you have heat change with change in temperature? Okay, so remember, when a system only contains one phase, solid, liquid, or gas, the temperature will increase when it receives energy. Okay, so the rate of temperature increase will be dependent on the specific heat capacity of the phase in the system. So different phases have different heat capacities. But what are specific heat capacities?
Ano, kailangan ko pa bang i-explain sa'yo?
The specific heat capacity is defined as the amount of heat required to raise the temperature of a mass of a substance by 1 degree Celsius. Okay, so when the heat capacity is large, the temperature increases slowly because much energy is required to increase its temperature by 1 degree. So it is also equal to the amount of heat lost by 1 gram of substance when its temperature drops by 1 degree Celsius. Thus, the slopes of temperature increase for the solid, liquid, and gases are different. So water, as an example, has the following heat capacities. In liquid phase, it has 4.18 joules per gram degree Celsius. In water, it has 2.06, and in gas phase, it has 2.02. So please remember this. Now, the heat change for this process is given by the formula Q is equal to mcat, so that it's easier to memorize. So M here represents the mass of sample in grams, remember? Then this one is the specific heat capacity, and this delta T is the change in temperature. So we get this by subtracting final temperature minus initial temperature. Okay, now let's try to solve a problem.
Listen, look, and listen, and
You
learn.
found a piece of copper metal weighing 3.10 grams embedded in an ice block. How much heat is absorbed by the piece of metal as it warms in your hand from the temperature of the ice block at 1.5 degrees Celsius to your body temperature of 37.0 degrees Celsius? And this is the constant. Okay, so first you have to write the given. So you have mass of 310 grams. Okay, how about the delta T? You have here from the temperature of the ice block at 1.5. So it's from, so this is your initial temperature, 1.5 degrees Celsius. And your final temperature is 37.0 degrees Celsius because it's to your body. So it's important to analyze the problem. You are also given the specific heat of copper is equal to 0.385 joules per gram degree Celsius. Now, just write the formula. Q is equal to mcat. Then substitute the values. 310 times this one times the change in temperature, final minus initial. This will give you 42.4 joule. It's the correct significant figures, so this is the final answer. Okay? Now let's combine everything.
No, ma'am.
So this diagram shows the heating curve of water. Let's have a scenario to make it easier to understand. Let's say you have an ice cube, okay? So which process will take more energy? Is it the melting of the ice cube or the conversion of water to steam? The short answer is that more energy is needed to convert the water to steam. The long answer is really a question. First, how do you get from one point to the other? Or what is the temperature of the ice? Or what is the mass of that ice cube? So a lot goes into taking the material from the starting point to the end point. So this graph here shows ice at negative 30 degrees Celsius being converted in a five-step process to gaseous water at 140 degrees Celsius. So how many steps? Again, one, two, three, four, five. So the same concept applies a while ago. So all the slopes, there will be change in temperature and change in kinetic energy, and all the flat segments will have a phase change. Okay? So after learning the change of state and specific heat calculations, it is now possible for us to calculate the heat absorbed during that entire process. Okay, so let's discuss first what happens here. So in the first step here, number one, ice is heated from negative 30 to 0 degrees Celsius. So ice here is at 0 degree Celsius. Okay, so to compute for the heat absorbed, we use the formula Q is equal to mcat. Okay, remember because it's a slope. Okay, so in step two, ice is melted at 0 degrees Celsius, giving us water at this point. Okay, phase change, it's a flat segment. So we can solve the heat here using Q is equal to N moles times the heat of fusion. Okay, step 3, you will have water at 0 degrees Celsius being heated to 100 degrees Celsius. So you have here water at 100 degrees Celsius. So to compute this, it's a slope. So we have Q is equal to m cat. Okay. Now, step 4, you have a phase change. So water at 100 degrees Celsius will be converted to steam at 100 degrees Celsius. So it's a flat curve. So the formula will be Q is equal to N heat of vaporization. Okay, so the last step is steam at 100 to steam at 140 because that is the goal. So there is another slope. So the formula is Q is equal to M specific heat times the change in temperature. Okay, so to summarize, all the slopes will have the formula Q is equal to M cat. Flat segments will have Q is equal to moles times the heat of X. X can be fusion or vaporization. Okay, this figure summarizes all the formula and the steps. Okay, now let's try to solve a problem.
Wait lang po.
Calculate the energy to heat 12.0 grams of water from negative 100 degrees Celsius to 200 degrees Celsius. So I put here the constants, the heat capacities, and the heat of vaporization and fusion. Okay, and here are the steps that we have discussed a while ago. So the last step after doing this, you have to add all of the values together, okay, to get the Q total. Step 1 is this one. Q is equal to MCAT. Okay, so substitute the values 12.0 grams times the specific heat of ice because this is the solid part times the change in temperature which is from negative 100 to 0. So that would be final minus initial. So 0 degrees Celsius minus negative 100. This will give you a value of 2,530 joules. Or in kilojoules, it will be 2.53 kilojoules. Okay. Number 2, we are now here. Phase change. So the formula that you're going to use is the moles times the heat of fusion because it's melting. Okay, so you are given grams of water and the molar heat of fusion in moles. What you have to do is to convert this in moles. Hence the N here. So 12.0 times the molar mass of water. If you're unfamiliar with how to solve the molar mass, we have a video for that. Then multiplied to the heat of fusion. Cancel the units. This will give you kilojoules. Final answer is 4.01 kJ for step 2. Okay. Step 3, we're here. So it's a slope, so we have Q is equal to MCAT. Substitute the values. Specific heat of water, liquid area. The temperature will be 100 because this is your final temperature minus your initial, which is 0 degrees Celsius. This will give us 5,020 joules or 5.02 kJ. Number 4, this one. Flat segment, Q is equal to N, heat of vaporization. Okay, it's the boiling area. So just the same as step number 2, convert, I shortcut it. This will give us 27.1 kilojoules. Step 5 is this one. It's a slope 12.0 times the specific heat of steam. Change in temperature, which is 200 minus 100. This will give us 2,400, and to follow the correct significant figure, have 2.40 kJ. Now this is not yet the final answer because you have to get the Q total. Okay, so add everything. This will give you 41.06 kJ or 41.1 kilojoules.
May sasabihin ka?
Calculate the amount of energy in kilojoules needed to heat 346 grams of liquid water. So let's write it down. From 0 degrees Celsius, so we have initial temperature, to 182 degrees Celsius. Okay, so assume that the specific heat of water is 4.184 joules per gram degree Celsius, and this is the specific heat of steam. So how many stages do we have? So to make it easier, this is a suggestion. You graph first. If you remember our graph, it's like this. 1, 2, 3, 4, 5. Then identify your starting point. It says here it's liquid water from 0 degrees Celsius. So you will start here, step 1. Then step 2 will be evaporation of water to 100 degrees Celsius. Step 2. And your steam from 100 to steam at 182. So we have a three-step problem. Okay, let's start with Q1. Q1 is a slope, so QM cut, substitute the values, specific heat times the change in temperature, 100 minus 0. This will give us 145 kilojoules. Okay, initially you will get joules, but I already converted it to kilojoules. Let's have Q2. Q2 is this one. It's a flat segment, so you're going to use N times the heat of vaporization. Okay, why is it vaporization? Because it's the second flat segment and you are actually in the boiling area. Okay, so substitute and convert times the heat of vaporization, which is equal to 40.79 kilojoules per mole. Cancel the units, so it'll give us 783 kilojoules. Q3 is the slope, so we use QMCAT. Then substitute the values. Specific heat of steam times change in temperature minus 100 because you are here. Then compute, this will give us 56.5 kilojoules. Then compute for the Q total, you just have to add everything. This will give us 985 kilojoules. Three significant figures. This is our final answer. Okay, so let's go back to the question. How does a phase change in energy affect phase changes? We already have discussed what happens when heat is added, right? Now, what if we have the release or removal of heat? The removal or release of heat results in two ways. First, there will be a decrease in kinetic energy of the particles. So the motion of the particles slow down, and this is accompanied by a decrease in temperature. Or second, the forces of attraction are formed, and a phase change may occur. So here, no change in temperature is observed. Now, if you notice, it's the complete opposite of the addition of heat or the heating curve. Now, we call this the cooling curve. Okay, and the cooling curve looks like this. Just like heating curves, cooling curves have horizontal flat parts where the state changes from gas to liquid or from liquid to solid. So these are mirror images of the heating curve. Note that the melting and freezing occur at the same temperature. So during freezing, energy is removed, and during melting, energy is absorbed. So let's try to solve a problem. How much heat is released when 10.0 grams of steam at 125 degrees Celsius cooled completely, take keyword completely, into ice at zero point zero degree Celsius. So the first step is to label the parts. Water has 100 degrees boiling point and 0 degree melting point. It says here that your substance is steam at 125. So we start here, 100 degree, and we want to go to ice at 0 degrees Celsius. So ice at 0 is here. Now it says here completely. If it doesn't indicate the completeness of the process, your sample will just be here because this is where the water freezes. Okay. But since it says completely, you have to consume everything. So that's one of the tricky parts. Okay. So how many steps do we need? We have one, two, three, and four. We have the steam at 125 to this one, steam at 100, steam at 100 to water at 100. Number three is water at 100 to water at 0, where it freezes. Then number four is water or substance at 0 to liquid at 0. Now let's try to solve. Okay, Q1. Q1 is a slope. So MCAT, then substitute the given times the specific heat of steam, which is 2.101 joules per gram degree Celsius. Then the change of temperature, 100 minus 125 degrees. Cancel the units. This will give you negative 5030, or in kilojoules, it's negative 0.503. Q2, it's a slope. Remember, this time it's a cooling curve. In the heating curve, we use the heat of vaporization. But now, we're going to use the opposite of vaporization, which is the heat of condensation. Now, what is the value of heat of condensation? It's the negative of heat of vaporization. So we can write Q2 like this, or the negative of H vaporization. So substitute the values. Okay, again, 18.02 is the molar mass times the negative of heat of vaporization. This will give you negative 22.6 kilojoules. Now let's go to Q3. It's a slope, so MCAT, substitute specific heat of times the change in temperature. This will give us negative 4180 joules, or converting it to kilojoules, it's negative 4.18. Now Q4, last step. So this time we need freezing. Okay, remember in the heating curve, it's heat of fusion. Okay, so this time we need the heat of freezing. And what is the value of heat of freezing? It's the negative of heat of fusion. Okay, so we get Q4 using this formula, or this one. Okay, so substituting the values, 10.0 times negative 6.01 kJ per 1 mole. is equal to negative 3.34 kilojoules. So if you notice, all of the values here are negative because this is a cooling curve. So to get the total heat released, you have to add everything. This will give us negative 30.62 kilojoules. So following the correct significant figures, this is only negative 30.6 kilojoules. To summarize our discussion, since temperature is a measure of average kinetic energy, any change in temperature is a change in kinetic energy. So again, all of the diagonal line segments on heating or cooling curve show a temperature change, and therefore a change in kinetic energy. So during these regions, a single state of matter exists and the sample is either getting hotter or cooler. During the horizontal line segments, there is no change in temperature, so kinetic energy remains constant. However, all the energy that is absorbed or released is related to changes in potential energy. So remember the three P's, okay? So plateau is equal to phase change, and you have a potential energy change, okay? And that's the end of our lecture.